Okay. Before starting the discussing the symmetric key crypto systems, block cipher, stream cipher examples, let us introduce cryptographic security. What we mean by cryptographic security? So we follow Karshav's principle. It states that adversary means the opponent, the third party. He knows the algorithm that is used. Only secret is the secret key. So in asymmetric key encryption, already we have discussed that encryptor and decryptor both have the same key. So the problem is to recover, the adversary's aim is to recover that key. So attack model, different types of attack models are there. Mainly we can divide the attacks into two categories, passive attack and active attack. Passive attack means essentially it can only eavesdrop. It can simply listen to the traffic but cannot alter or delete the messages like that. So here passive attack means the attacker can only listen to the traffic, see the messages, he cannot alter them. But in active attack, this is more severe attack. It can alter messages. It can replay the same message, delete messages, modify, insert, all these. Active attacker has all these capabilities. Now here the passive attack, it is categorized in not only passive attack, means here we have ciphertext only attack, known plaintext attack, chosen plaintext attack, and chosen ciphertext attacks. Okay, so chosen ciphertext only attack is, as the name says, you have access to a ciphertext. From that ciphertext, you have to find out the key, recover the key. Known plaintext attack, it says that corresponding to a ciphertext, you also know the matching plaintext. So you have a plaintext ciphertext pair. From that, finding out the key. Chosen plaintext attack is stronger attack. It gives the adversary temporary access to the encryption machinery. Encryption machinery means adversary can ask excite queries on the plain text of his choice and can get the corresponding ciphertext. And these queries it can make adaptively. Adaptively in the sense that adversary is submitting xi to the encryption machinery and getting yi. After seeing yi, he can determine the next query. What will be his next xi plus 1. So this way he has access to several plaintext ciphertext pairs. So adversary is given more power. From that, if the key recovery is not possible, then your scheme is the scheme is much better. Means it gives security wise, it is much better compared to ciphertext only attack. That is the scheme that prevents only ciphertext only attack, or the scheme that prevents only known plain text attack. So this is more stronger. Chosen ciphertext attack is the strongest model, where adversary has given temporary access to the decryption machinery. Okay, so adversary can submit, adversary can query to the decryption oracle ciphertexts and get the corresponding plain text. And adversary can make these queries adaptively. This is actually the strongest notion of security. So adversary can choose a ciphertext string y and corresponding plain text he can get. So adversary has access to several plain text ciphertext pairs. From that, adversary's goal is either to recover the key or it is distinguishing attack. Distinguishing attack means whatever key you are whatever information you infer from that, whatever key you are recovering, that is indistinguishable from a random key. Adversary cannot distinguish this. Distinguishing attack means adversary can distinguish it. Distinguish the key from the random key. A malleability attack, adversaries holds malleability attack, other application specific security goals adversary can have. Okay, so for example, with Hill cipher, I am going to discuss the known plain text attack. This Hill cipher does not survive the known plain text attack. If you only apply the ciphertext only attack, it is difficult to break. So in the Hill cipher, if you can remember, Hill cipher, we have m-bit plain text and key is m cross m invertible matrix over Z26. So while you encrypt x, simply you multiply x with the matrix key. So you get m-bit ciphertext, m digit ciphertext. Digits are from Z26, modulo 26, and decryption is simply this. So given this ciphertext, finding the key is very difficult. But if you have a pair, ciphertext plaintext pair, plaintext ciphertext pair, as the case in known plaintext attack, we can break this scheme. How? Let us illustrate this. Let us illustrate this. So essentially, what we do. So this is the encryption machinery, encryption method. So x is multiplied by the columns, first column of k. This is the first entry of y. Then second column of k. When you multiply x with second column of k, you get this. So essentially, this y is generated. The elements of y, two entries, not only two. This is m entries. M entries of y. How we are generating? Each entry of m is generated taking an affine transformation. Each entry in y is generated in this way. Generated taking the linear combination of the columns of k. So if the column, ith column of k is k, 1i, k, 2i, k, mi, then yi is generated taking this linear combination of x1, x2, xn with this k, 1i, k, 2i, k, mi. So x1, k, 1i, x2 plus x2, k, 2i plus. So this is essentially affine cipher, affine function in the variables x1, x2, xn. So yi's, these yi's are linear combinations of x1, x2, xn with coefficients, ith column coefficients of k matrix. So if you know xy pair, then you can calculate this k. So k is essentially x inverse y. K equal to x inverse y. How can I do that? Let me illustrate this with example. Suppose you are given this plain text ciphertext pair, and you are given m equal to 2. Okay, your block length is 2. So Friday, this plain text is encrypted to the ciphertext this PQCFKU. Okay, so we have one-to-one correspondence among the characters, English alphabetic characters, and the integer 0 to 25. So using that, I can get these equations. So P corresponds to, so M equal to 2, so FR encrypted to PQ, ID encrypted to CF, AY encrypted to KU. So we get this. PQ corresponds to, PQ is the ciphertext, PQ corresponds to 1516. So 1516, how we generate? The ciphertext is generated in this way, y equal to x into k. So 1516, this is my y, 1516 equal to encryption of FR. F and R, F is 5, R is 17. 517 is multiplied with k. Similarly, ID and CF, it will give me this equation, and KU, AY, this will give me this equation. Okay, now K is essentially, this key is a 2 cross 2 matrix, invertible matrix over Z26, such that this relation holds. So from these two, I can get the equation, get this equation. So 15, 16, 2, 5 equal to 5, 17, 8, 3 K. So you can easily check that. You can easily check that. So this one, how you get this 15? 15 is obtained by multiplying the first column of K, multiplying 517 with the first column of K. So multiplying 517 with first column of K, it is giving you 15. Similarly, 16 you give multiplying 517 with the second column of K. So multiplying first column, multiplying 517 with second column of A will give you 16. So this matrix, I can write these two equations into this matrix form. Now you find K. K is simply this inverse this. So when you find this calculation is shown here. When you find this, you need determinant inverse. Determinant is essentially 9. Determinant, if you find the determinant, this is 15 minus 136. 15 minus 136 is 15 minus 136 is minus 121, and you have to work over modulo 26. So you divide it by 26, take the remainder. So minus 17 modulo 26. And minus 17 over Z26, it is simply 26 minus 17, that is 9. So you have to, this inverse is this adjoint matrix divided by the determinant. Determinant is essentially 9, so 9 inverse you have to find. So 9 inverse, you have to find modulo 26, you can check, this is 3. Okay, so there is extended Euclidean algorithm. You can apply that also to find this. We will discuss that algorithm, as I said earlier also. So for 26 is very small, you can apply the exhaustive search and try out 9 multiplied by which element from Z26 give you 1. Okay, that way you can find 9 inverse. So you can calculate, you can check that my K is this. So it might happen that these equations, fortunately, I get this determinant non-zero. Means it might happen that your equations are such that the inverse does not exist. This x. This is essentially capital Y equal to capital XK. So it might happen that this X inverse, this matrix inverse does not exist. So in that case, you have to take other two equations to construct this matrix equation. Okay, so it is mentioned here. In general, you have your so if you have m block matrix, m block size m, then you have to find out m cross m matrix K. So suppose xj is x1j, x2j, xmj, yj is y1j, y2j, ymj. So this matrix equation, you have to find K is m cross m matrix. X also, you need to find this m cross m matrix, you have to take m equations to construct x and y, this relation. Okay, so you take this m cross m, define m cross m matrix, x equal to xij and y equal to yij. M distinct plain text ciphertext pairs you are going to need. Okay, M distinct plain text ciphertext by xj, yj, x1, y1, x2, y2, xm, ym. Suppose each xj is a block of length m, each yj is a block of length m. So you construct m cross m matrix in that way and then find the inverse like x inverse y, k equal to x inverse y. Now it might happen that whatever equations you have chosen, that might not give you the answer. This x may not be invertible. In that case, you have to try other sets of m plain text ciphertext pairs. Okay, Okay, so this example, first two equations fortunately works. So it's okay. Now, okay, it's fine. Now let us now discuss symmetric key encryption. Already we have discussed this. Encrypt to encrypt a message, use a secret key, and ciphertext is produced. It is sent over a public channel. And decryptor uses the same key to decrypt the ciphertext to get back the message or plain text. Adversary is a third party who can see the ciphertext that is sent over the public channel. So his goal is to find the key. The encryption algorithm, whatever encryption algorithm, matching decryption algorithm rules we are using, that are all known to the adversary. Only secret is the secret key that adversary wants to find out. That is actually Karshov's principle. Now, symmetric key crypto systems are broadly classified into two: block ciphers and stream ciphers. These are the two types of symmetric key crypto systems or secret key crypto systems. Secret key because both the encryptor and decryptor uses the same key. Now, the block cipher, what we do on block cipher? Suppose you have a plain text string x equal to x1, x2 like that. So x1 is a block, means a whole plain text string is divided into blocks of same size. x1, x2, x3 all are having the same size. Okay, so successive plain text elements are encrypted using the same key. So your key is K, plain text blocks are x1, x2, x3, etc. Then ciphertext is generated using means encrypting x1 with the key K, encrypting x2 with the same key, encrypting x3 block x3 with the same key, like that. So ciphertext string, produced ciphertext string is essentially y1, y2, y3. Those are essentially encryption of x1 using K, encryption of x2 using K, like that. So examples of block ciphers and stream ciphers are SPN, substitution permutation network. We are going to discuss this. DES, data encryption standard, Ringdale, AES, advanced encryption standard, IDEA, RC6, and many more. So I will discuss SPN today. Okay, SPN. So how it works, let us discuss this. SPN and also DES, I think I can cover today. Maybe let me try with SPN. Okay. Now in block cipher, R-round block cipher, this is the general rule how a R-round block cipher is constructed. So as I said that block cipher uses the same key. So from that key, same key K, you produce round keys. For R round block cipher, you have to produce R round keys by using some publicly known key scheduling algorithm. For SPN, I will explain this. Okay, how this key scheduling algorithm, in which way these round keys are generated for SPN. So first job is from the given key, you find out these round keys using some publicly known key scheduling algorithm. If you know the key, you can generate this. If you don't know the key, then you cannot generate this round key. So to generate this round keys, you need to know the key. The encryptor, decryptor having the key, they can generate this round key. Now, so initially your plain text x0 is essentially your plain text. X0 is x. So this is written here. X is plain text, and fi is round functions. Round functions for all the rounds. For all the rounds, round function. This is essentially this whole thing f. Okay, this is we are using different f's, fi's, f1, f2, fr. They may be same also. Okay. So xi, we generate xi this way, fi xi minus 1 ki. So X is plain text, F is round function for all rounds, encryption operation. So X0 is X. So initially it is X, and then this plain text and first round key, you evaluate the function using X0 and K1. You get X1. Then this X1, then this X1, then this X1, and the second round key K2. Using these two, you calculate F2 of this. That is actually your X2, like that. Okay, so you apply this. So initially X0 is X, then X1, to produce X1, this should be F1. According to my figure, I have used several different functions for each round key to operate with each round key. So this is F1, X0, K1, then X2 is produced using F2, X1, K2, right? XR, rth value, rth round KR is used, and previous XR minus 1 value is used to calculate it. Finally, this XR is the ciphertext. For decryption, we need this function to be invertible, and we need this feature explicitly. This Fi is invertible when we fix Ki. So these F functions that are used here, these F functions, these Fi's should be injective if its second argument is fixed. Second argument is this key. If you fix this key, this is invertible. This way, these functions are constructed. So there exists a function F inverse such that F inverse f of x y comma y equal to x. Okay, so to design these functions vary. For SPN, it is these functions are something. For DES, these functions are something else. For AES, these are defined in a different way. To design these functions vary. Not only these functions vary, design to design, this key scheduling algorithm is also varies. Okay, so decryption is now straightforward. So you have the decryptor is having the ciphertext. So this is essentially y is essentially XR, and then you apply F inverse. So if you apply F inverse XR comma KR, it is giving you XR minus 1. F inverse X2 K2 giving you X1, like that. Ultimately you get whatever X0 you get, that is essentially your plain text. So the whole thing depends on how you construct your F. This F should be constructed so that this condition is satisfied. This condition is satisfied. Second component, second argument of F, when you fix it, it is invertible, and using the same key Ki, if you this is suppose F of x Ki, F x y, this is F of x y, and using y, F inverse is giving you back x. So this functionality is needed. You have to design this function. So this is your R round block cipher. For SP, so this is essentially called iterated cipher. R round block cipher, or it is called iterated cipher. So we are using iterated cipher. So iterated cipher needs specification of the round function, F1, F2, Fr. These are the round functions, and specification of the key scheduling algorithm. How to generate your round keys from the given secret key. So these two we need while you design such iterated ciphers or R round block ciphers. And encryption of a plain text will proceed using R similar rounds. Okay, these two, when satisfied, we call the cipher is iterated cipher. So SPN, for SPN, this is substitution permutation network. SPN, substitution permutation network. So already in classical crypto systems, we have explained how the substitutions are used and permutations are used to design different ciphers. So in combination, SPN uses these in combination. So sequence of permutations and substitution operations are used in SPN. So this is suppose you have L bit plain text, and by using some key scheduling algorithm from the key k, you find the keys k1 round keys k1, k2, kr. Okay, so each are L bit strings. So first, what you do, L bit plain text and L bit this round key XOR L bit string is produced, and then you use a substitution. Use a substitution. This pi s is this is essentially S box, substitution box. So here L bit, each bit is substituted. Each bit for each bit we use substitution box, substitution cipher we are using. Okay, substitution cipher you use it. Then it produces L bit, and then these L bits are shuffled using a permutation. So use a permutation L bit shuffle, and L bit it produces L bit. So this is my x1. So in the first round, this is my f function. In the f function, we do in this way. So x0 f function, it takes k1. So if you just take the previous one, this f function uses x0 and k1 produces x1. Here also the same thing. This f function is essentially consisting of XORing first, and XORing your plain text with the L bit plain text with the L bit key, round key, and then you use substitution box, pass it through the substitution box, and then you permute. So this is your f function. So L bit x1 is produced. Then in a similar fashion, you operate on x1 in this way. X1 is XORed with k2, second round key scheduling, second round key, and then passes through the same substitution box, and it may be different. Means for SPN, different S boxes may be used for different rounds. Different S boxes may be used for different rounds, and different F functions may be used for different rounds. So for SPN, we use the same function. Every time same S box, same permutation, every time is used. Every time same permutation, same S box are used. Pi S is the S box, pi P is the permutation. Okay. So as I said, so for each round in SPN, same F function is used. Same F function is used. Okay, because its function depends on XOR, pi s and pi p, and for every round this pi s and pi p are fixed for SPN. But it might happen that different S boxes may be used, and it will produce different F functions. So if you use different S boxes, S1 here, S2 here, our permutation also different permutations, then F function must be different in that case. So we will see later DES, data encryption standard, it uses different S boxes for different rounds. For different rounds, it uses different S boxes. And for AES, advanced encryption standard, this uses single S box. Every round it uses the single S box for all rounds. And in addition to substitution box it uses, in addition to permutation operations, it uses invertible linear transformation in each round. Okay, so for AES, these F functions are different. For DES also different. For DES, why it is different? Because these S boxes are different. Different S boxes are used. For AES, why these F functions are different? F1 here, F2 here, because substitution box same, but permutations also, it uses permutations, but it also uses invertible linear transformations in each round. In each round. Now we will see where actually this F function differs for AES. S box same, addition means it uses permutation operations as well as invertible linear transformation. So here XOR, substitution and permutation. For AES, we use substitution, permutation as well as linear transformation like Hill cipher or affine cipher. Okay. Now key scheduling for SPN. So your permutation is L bit string. Substitution box is L bit to L bit. and permutation is LM bit to LM bit. Okay, so plain text and ciphertext both are LM bit strings, and key is a key space is a subset of this. Now for SPN, what is the key scheduling algorithm? With one example, let me explain it. So here, from initial key, using key scheduling algorithm, you produce round keys. There are R+1 round keys. K1, K2, K R+1. R+1 round keys. For R round SPN, K R+1 round keys. Okay. For example, if your initial key is 32-bit string, and you specify your L, M, and R all to be 4. Then, as I said, these round keys are essentially LM bit strings. So these round keys are essentially 16-bit strings. L into M 16-bit strings. K1, K2, K R+1 16-bit strings. R is 4. So from this 32-bit key, we produce 5 round keys. K1, K2, K5. Each is 16-bit string. Now, how we generate this 16-bit string? This is very simple. In SPN, we do in this way. This key scheduling algorithm is like this. So this is 32-bit. So K is K1, K2, K32. So this K1, we take a first 16-bit. From K1, we take first 16-bit. K2 is from K5, the next consecutive 16-bit. So K1 is means this round key K1. I have 5 round keys. First round key is obtained by taking the first 16 bits from K1, K2, K16. The second round key, how I obtain? From K5, starting from K5, you take 16 consecutive bits from this key. So this way we construct. So the construction is this: ith round key is 16 consecutive bits of K starting from the position K 4i minus 3, I from 1 to 5. So if you take I equal to 1, K1 is simply from K1 to 16 bit. The K2 is, if I take 2, K2 is K5 to 16 bit. K3 is K9 to 16, up to 16. K9, K10 up to wherever 16 bits stops, you have to do that. So when you take K5, it is essentially when you take I equal to 5, so it is 17, K17 to K32 last, up to last. So that will give you 16 consecutive. So this is the key scheduling algorithm of SPN. Okay, if you take L, M, R to be 4, 5 round keys generated from the given key in this way. So if you know the key, this key scheduling algorithm is known. Once you know the key, you can always generate this round keys. If you don't know the key, you cannot generate this round keys. Okay. Okay, so here. So SPN for this specification, I have taken L, M, R to be 4. So your plain text, ciphertext, both are essentially LM bit strings. That means 16-bit strings. So in SPN, these 16 bits. So as I said, your 16-bit, this is essentially 16-bit strings. This is, instead of L, this is LM bit. Okay. So 16-bit strings first XORed with the 16-bit K1. 16-bit strings XORed with 16-bit round key, first round key. Then it is substitution passed through the substitution box, PIS, and then it is shuffled using the permutation. So it is shown in this figure. So in the next figure, So your plain text string is 16-bit. Round key, first round key is also 16-bit. So initially what you do, your plain text is 16-bit. 16-bit, we divide it into 4-bit, 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 4-bit. So this is your W1, first round. Your W1, I denoted by W1. This is your X. Then you XOR it with the round key, 16-bit round key, K1. 16-bit round key K1, whatever produced, each 4-bit is passed to the substitution box. Each 4-bit is passed to the substitution box. So this is this substitution box also I think is given. This substitution box. This is your. So I will explain it later. So I have 4. So the 16-bit plain text XORed with 16-bit key, then passes to the S box. So same S box, 4-bit, 4-bit, 4-bit. So 16-bit. So initially it was WX. After XORing, I call it U1. That is W1 XOR K1. And then after passing through the S box, I call it V1. That is essentially pi S of U prime. Okay, then I have to apply the permutation. So when you apply the permutation on V prime, you get this W2. This was W1. Then it is the next round. It will pass instead of X. It will be W. It will be ready to go for the next round. So we are shuffling now. While shuffling, this shuffling pi p. This is a permutation. This is a permutation from all the 16 elements. This in the mind that this substitution is, if you check this substitution is L bit to L bit. L is 4, this is 4-bit to 4-bit. Substitution box is taking you from 4-bit to 4-bit. But the permutation is 16 to 16. Okay, so here 4-bit passes through the substitution. Now you get 16-bit here. This 16-bit is permuted. So 1 bit goes here, 1 bit goes somewhere here, 1 bit goes somewhere in here, 1 bit goes somewhere here. Similarly, for this one also, 1 bit straight according to this, another here under this, and another this position. These positions are shuffled. Positions are shuffled. One position goes here, one position here remains here, one position goes here, one position goes here. This way it is set pi p. So once so XORed passes to substitution box, then permuted. So you get W2. Then again XOR with second round key, pass through the substitution box, and then shuffle. Use the pi p. So this way I have 5 round keys. So K2, then K3 also do the same thing. Whatever after pi p, whatever you get, that is essentially W3. So W3 and K3 you XOR, pass through the. So you get U3. You apply pi p. You pass this U3 through the U3 to the substitution box, you get V3, and on V3 you apply pi p. You get W4. So W4 K4, again do the same thing. Now in the fourth key, when you apply the fourth key, K4 and W4 you XOR, then pass to the substitution box. So in that case you don't shuffle at this step. So this step shuffle is not used. This pi p is not used. So it is directly whatever you get V4 is not permuted. So V4 is simply XORed with K5. This is your ciphertext. Okay, so for permutation we use, as I said, permutation is over the 16 bits. So the bits are essentially 1 to 16. So it is mapped in this way: 1, 2, 3, 1 position goes in one position, 2th position goes 5th position, 3rd position goes 9th position, 4th position goes where. You can get these specifications are given. So you can take Stinson, the book of cryptography book of Stinson. There you can get all the specifications. And the substitution cipher, this is L-bit to L-bit. This is also this is L-bit to L-bit. For JET, means we have actually 16 bits. Those are encoded as 0, 1 to in hexadecimal 0, 1 to 9, and then A to A. And substitution box, these positions are in this way. Okay, so we have for SPN the design we have specified, and this pi p and pi s, you check the book. Okay, these are, or you can check net. These are all available. These are all available. Okay, let us stop here. Okay, in the next class we are going to discuss Feistel cipher that is used for encrypting the DES, data encryption.